Okay, so welcome everyone to the meetup. I want to thank Sagnik for his being here today with us, and I think I will just give the mic to you.
Okay, so I think I'm going to share my screen, okay, and then we can go from there. Okay, so can you see my screen? Yeah, I think you can see the screen, right? Um,
Yes, we can.
okay, so so my name is Shagnik, and so today I think uh, so. First of all, thank you for inviting me here, and I'm very glad to sort of meet with you and discuss our work. And this is a work that we presented in Calling recently. So the talk will be about a couple of things. One, so because it's a longer time, and I thought it might be, when you present the paper in the conference, you don't get to talk a lot about the basics that you used to in that paper. So I thought might be interesting to kind of discuss the basics and then go into the techniques that we have, those basic techniques that we have used in the paper. So my name is Shagnik, and I'm currently a research fellow at the University of Michigan. And so let me go to the next slide. So currently I work on sort of generalizability of NLP DNN models in clinical and biomedical NLP tasks. And I also work on explainable few-shot methods for information extraction. So this work was done while I was a postdoc at the University of Copenhagen, and I worked on explainability of DNN models in multi-hop reasoning problems, so such as question answering, which is one of the examples I will use today. Previously, I was an AI engineer at a company called Interactions LLC, where we worked on dialogue systems and DNN models for information extraction. So broadly, my research interest is to see, I think the one-line summary would be how reasoning emerges in connectionist architectures, which of obviously DNN models are one examples of that. So, and beyond work, I kind of I'm very interested in history, and like to travel, and I play a game called cricket. I don't know if you guys are familiar with that. It's a very Indian thing. So I don't know if you're playing that, but so this is like about me. And again, so I'm very grateful for this opportunity, and I hope that we all get something from this talk, and there are some research directions and possible collaboration opportunities and so on. So the structure is, as I said, it will be a brief intro about DNN explainability focused on NLP, and so that will be the first, I think, 12 to 14 slides. And if this is something that you already know, then probably this is not going to be very interesting. But from the talks that I looked at to YouTube, there wasn't like a discussion on explainability, so I thought this would be something that might get interesting. And then we'll go to the paper, which is the kind of the focus of the talk. So the first thing that we want to know is like what is an explanation and why we might need it. So we have two types of models these days. One is like an interpretable model, which is typically a linear model where each feature can be assigned a weight. And so, for example, the coefficients from a logistic regression model. So non-interpretable models like nonlinear models and DNNs. And so typical use case that we always use is that suppose your company wants you to automatically assign job applicants to teams, and then the features that you have are from text and other personal information, and you accidentally somehow train your model on a data set where most engineering applicants are male and most HR applicants were female. And now the model will probably put every male applicant to engineering and get very high test accuracy, but you obviously don't want that. So for an interpretable model, we can check if the gender feature has a very high weight. And but so we also should be careful about this. And for example, if you're using logistic regression and all variables should be brought to the same scale. So consider a scenario where one feature is an integer and the rest is binary. So even when the binary feature has a larger coefficient than the integer one, it will have less importance. But in the DNN domain, what we are mostly, especially in text, what we are mostly interested in is a question that which part of an input is important for the output. So, for example, if you see a sentiment classification task, it's like, let's say there's an intelligent fiction about learning through cultural clash, and so if the model outputs a positive, then why does it do that? How important is intelligent for the positive class? How important is fiction for the negative? If it does negative, how important is fiction for the negative class? And this is a bit different from the traditional classification scenario where we have like n sentences which are converted into a matrix of n cross v dimension, and the feature vectors are v dimensional, so there are like v coefficients if you are fitting a logistic regression, not exactly v but some in the order of that. There are v coefficients if you're fitting a logistic regression model, and then we get important features for the entire task. So and this is not what typically is done in the interpretability literature in DNNs. Here the explanations are input based, like for each input. So we are basically in what we're doing is we're producing a saliency score or an importance score for each token. And this is a post hoc measure of importance, obviously, because we have the model and we are trying to say how important the token weight is in getting that output. And the question is like, how do we evaluate if this is truly what is important for the model? In other words, how to measure the faithfulness of the explanations. And there are two important distinctions. One is faithfulness versus plausibility. So faithfulness is how close it is to the model reasoning process, versus plausibility, which is how close it is to the human reasoning process. So to give you an example, so this is a good movie. Let's say this your model predicts it as positive, and you get good as a high, and somehow your explanation method tells you that good has a very high saliency score, the token good. So it is plausible, obviously, because as a human, you know that is what typically makes it a positive sentiment. But it might not be faithful, which means that it might not be what the model actually used. So unlike most machine learning algorithms, the faithfulness of an explanation cannot be measured by humans, and so typically you cannot have like a gold standard data set on which you will evaluate these algorithms. So, but the plausibility can be. So we are mostly going to be concerned with faithfulness in the explanation, in the evaluation, and the faithfulness evaluation is actually based on a couple of assumptions. So for example, one assumption, let's say the very strong assumption that we sometimes make, is that the two models will make the same predictions if and only if they use the same reasoning process. If you agree to this assumption, then you can use something like simultaneity. So in a simultaneity evaluation, you have a model M, which has input I, output O, explanation E, and then you have another model, M dash, and then you give it the input and the explanation, and the model now must correctly simulate the other model's output, the first model M's output. And M dash can be a human. So basically, instead of using using M dash, using another model, you can ask a human and tell them that, okay, the model produced this explanation, and on this input, will your output now match with the model's output? That's one set of assumptions. That's one assumption and sort of evaluation criteria based on that, evaluation metric based on that. So there is another evaluation, typically what we do, and this is based on the assumption that the contributions of different parts of the input are independent of each other. And this, if you make that assumption, the evaluation is fairly straightforward, which is basically you have an original input, and then you have a predicted score, which is typically the probability for a class, and your explanation is a set of tokens. And what you're going to do is you're going to produce something called X dash, which is tokens after removing the explanation, and then you have a predicted score for class I. So the original, so you basically calculate the score for after removing the explanation, and then on the original one. And the difference is what tells you how much is the what was the comprehensiveness of the explanation. So if you, and the sufficiency of the explanation is, if you just took the explanation tokens and predicted a class label using the same model, what does it, how will the probability change? So these two things are used very much in the exploratory literature for, and they are all based on this idea of getting a getting the explanation tokens and then either using them to predict or removing them from the input and then predict. And so we'll use something like that later on. So for, so I think I'm going to use two methods in the paper. I use two methods, and so I'm going to go briefly over these two methods. One is called occlusion, and so the occlusion idea is very simple, and I think this is originally came from the paper called representation eraser, and that's, I think, from 2016 or something, from Chris Manning's group. So it's very simple. You take a model, and the model has a confidence code for each class, and then we part of the original input by removing a token, and measure the confidence of the classifier on the part of input, and rank the tokens in that order. So whenever you remove a token, if that reduces the confidence too much, then that token was important for the model explanation. So that's one. That's how the occlusion method works in general. So there's obviously some problems with occlusion. One is that we can get the saliency score of a token for for a class level by occlusion, but sometimes like multiple tokens are important together. So for example, if you have a sentence like "this movie is not good," obviously the not good part is important together, and not just the token good or token not. And that's kind of a fundamental like design problem. But there's a implementation problem, which is we want the saliency score for each token, and then you have to run the inference code for each perturbation. So basically, if there are like n tokens, then you have to run the inference code n times, and obviously that's quite computationally expensive. So gradient based methods, they actually do solve these problems. And the basic idea behind the gradient based methods, that's quite simple. So let's say, what is the gradient of a function at a point x? So if f is a scalar function, then which is basically maps our d-dimensional vector to a single value, then each dimension of the gradient vector tells us like how much f would change with a unit change in that dimension. So obviously, higher this value is, the change in f is higher with respect to that dimension. So typically, a DNN classifier is a differentiable function which maps from Rd to Rc, where d is the dimension of the data and c is the number of classes. And f is a so that function f right now is a vector-to-vector function, and we'll need a vector-to scalar map, and we'll call it f dash. So assuming that we can find an f dash, and if we consider each dimension of x as a feature, then the gradient vector values can be used as saliency scores, right? So because each of them, so what this vector is telling us is that if I change each of the dimensions, how much will the output change? So this is obviously maps well to the notion of importance. So for NLP, we have like two problems. So first, that the feature is an input token. So there are multiple possibilities for f dash, which is we can get the top prediction probability or the prediction probability for the class we are interested in. We can use the loss function. But I think the bigger problem is we have tokens. So your original input is n cross m, where n is the embedding dimension and m is the number of tokens. So when you differentiate, so basically you have a map from your f dash is mapping from our n cross m to scalar value. So we really get a matrix of dimension n cross m, and we need to reduce it across the dimension n to produce a vector of dimension m. So basically, you want the saliency score for each token. So you would have to do a reduction somehow across the embedding dimension. And there are multiple methods. So one is typically people use L2 norm and input cross gradient, but there is really no unified um, like a prescription to use to say that we should use this one versus the other. And in most papers I see people using something and then saying that the others were kind of similar. So we don't have a really good answer for which reduction method to use. There are some problems with the gradient-based methods. One is like something called saturated outputs, which leads to counterintuitive gradients. So if you have a function like this where you know x1 plus x2 equals, so y becomes constant when x1 plus x2 is greater than 1, then what happens is that neither the gradient is going to get 0, and then neither of the x1, the function isn't really depending on when x1 or x2 is 1, any of them is 1, then the gradient isn't depending on one of them, any of them. So this kind of problems, and there is a problem with discontinuous gradients, which is your gradient changes. You have a step function which changes very quickly. So at one point you have no dependence on the input, the other point you have very high dependence on the input. So these are the typical problems with gradient based methods, which is solved in a method called integrated gradient, which we're going to use. And the main idea behind integrated gradient is that the gradients are too local and so sensitive to small perturbations. And the improvement is we calculate multiple gradients with perturbations. So we want to calculate the gradient with respect to x, and we'll start with a base point x0, and then we take the gradients at a bunch of points x dash from x0 to x along a linear path, which basically means that the x dash points are monotonically increasing, and then we'll take an average. So it turns out that, so I'm not going to discuss this why, but it turns out that integrated gradient comes with some benefits, which is why it's called I think the original paper called it the axiomatic something, I forgot the exact title, but it satisfies two axioms. One is called sensitivity axiom, and one is the implementation invariance axiom. So the axioms are easy to explain, but why that happens in IG, that proof isn't quite easy to explain, and that's kind of outside the scope of this talk. So, but if you're interested, then you probably definitely can take a look. So the summary of this is that the gradient-based methods are kind of easy to implement. So if you have a differentiable function, all you really need is a backward call. And so we can define the backward call on the loss function or any scalar function that can be differentiated over the network. And so if you are interested, so the Captum is a library which has actually a lot of experimental methods, including gradient-based methods. And so you can take a look, but the fundamental idea behind gradient-based methods are quite simple. So this kind of ends the discussion about the background that we are going to use later on, which is actually the paper. And if you have any questions, I can take them now, or I can just go ahead. So I suppose not, right? Okay. So this brings us to the paper with and the broad goal of this work is to understand whether DNN models are right at the natural language understanding task for the right reasons. And this has been a question for a long time, and there's been a lot of debates about this, and I think this paper is a step in that direction, particularly for question answering models, and I'll explain why. So DNN based models, and particularly fine-tuned language models, they provide the state-of-the-art results in many tasks, and so machine reading comprehension or QA is like one of those tasks. So There are many papers that say that the models use shortcuts or heuristic methods to solve the problem. And in fact, the predominant belief in MRC experimental literature is that the models do use shortcuts. So I think there is a problem with that argument, which is the way this sort of this conclusion is, people come to this conclusion. So typically what I see in a lot of papers, people drop sort of kind of text and say that so that becomes now your, if you imagine that you have a question and a context, right? As a human, you need to read the whole context to answer that question. What people do is people drop tokens from that context, so now the context becomes unintelligible. As a human, you cannot really understand that context, and or the question, so they would drop the question tokens from the question as well. But the models seem to actually produce the right answers even from that mangled context. So that sort of brings people to the conclusion that because that input is meaningless, but the model is still producing correct answers, so the model must be using shortcuts. So there are like two problems with this argument. One is that most models are never, except for squad v2 or something like that, most models are never trained to produce a I don't know answer. So if you are perturbing, if you're mangling your input, and which makes the question unanswerable, you can no longer, but you didn't train the model to produce an I don't know answer, you cannot expect the model to actually produce a wrong answer. That's one. And the second thing that I think is important is that when you drop a token and the model answer remains unchanged, that doesn't mean that the token wasn't used. And because it might be that the model did produce the same answer but with a much less confidence. So you should really sort of define rigorously what you mean by a failure situation, or when do you say that the model, like when you, if you say that the model uses a shortcut, then you need to define a long cut or sort of expected reasoning steps. And so this paper is in a kind of a step in that direction. So specifically, we provide a framework for defining expected reasoning steps for our DNN model on two MRC datasets. And then we will use two post-hoc explainability methods to test for these reasoning steps in the models. So so the paper actually does discuss in details like what we mean by understanding. But so there's a section in the paper that discusses what it's mean by human understanding, what it's meant by model understanding, and so on. But in summary, there are two main components of human understanding, at least that's what we believe. Is one is creating new concepts and establishing links between existing and new concepts. So this makes it hard to map this definition to models, because humans cannot understand without proper conceptualizations, but the model will encode some information even when the weights are random. So we don't really know what the concepts are being created in the models. So arguably a better approach for this problem is to design a behavioral test, as Turing proposed in his paper. So the Turing test is, if you think about it, the Turing test is a behavioral test that is saying that I don't know if you actually understand me, but I can sort of compare your response with a benchmark, which is the computer. With a human. So we actually have defined such behavioral tests for benchmarks for machine reading comprehension, but as it turns out that many of them has turned out to be gameable, or basically people have been able to find shortcuts in that. So we need to define exact success criteria for this test. And I think the one thing that I'm trying to get across is that instead of saying that our model, so the model understands natural language, or something like that broad, we probably want to restrict ourselves in asking that, does this reading comprehension model produce its output based on valid information extraction and inference strategies. So that's the whole point of the paper, is that we kind of need to define exact steps that we expect the model to follow, and then we check for those steps. So as I said, that in general it is hard to define what is a valid reasoning. So as I said, in the if the definition of understanding also has a component of generalization, which means the model needs to use, if a model uses some strategies, it needs to use the same strategies in novel contexts. But I think more importantly, what constitutes a valid reasoning. So this is hard to define generally, and this is why we kind of restrict it. So we choose two machine reading comprehension data sets that require the skill of coreference resolution and comparison. So if you look at the examples, right, the first one is from a data set called coref, and as you can see, it would appear that one would need to resolve the pronoun I to goreki to answer the question. Similarly, the second question, which is from a dataset called 2wiki hub QA, one needs to associate the value 2003 to the movie Blind Shaft and 1932 to the movie The Mask of Fu Manchu, and then understand the earlier part of the question requires a comparison between these two values. I think more important, like a very interesting thing to see here is that these questions can be answered with heuristic mechanisms. For example, for the first question, if the only last name in the context is Goreki, the model can just output that. And in the second question, if the model can choose one of the entities in the context and still have a reasonable accuracy if the data set has that bias. So if all your data set, all your data points have the answer as the first entity, then the model can just choose that and still have quite a bit of high accuracy. So we don't want the models to do that, and therefore we define the expected reasoning steps to solve these problems. So I'm giving the expected reasoning steps in comparison questions. And so the first step is kind of similar to a semantic parsing of the question. The second step is to establish equivalence relation between the entities in the question and the text. And the last step is to perform the value comparison between the two values that needs to be compared, which is 1932 and 2003. So the paper describes these steps in further details and shows the expected reasoning steps for the coreference questions. So I guess my suggestion would be, if you're interested in the coreference part of this table, the paper does have that. But this is not the only possible formulation, but I think we believe it's a reasonable formulation of the reasoning steps that the model should take, or at least a human would take. The formulation is very similar to a recent paper called QED, and that overall the goal of our paper is quite different from QED. So what we are saying that a model doesn't have to follow these reasoning steps, but a competent human reader should find its reasoning kind of relevant to the problem post factum. So in other words, if model's decision process for this problem cannot be related to the spurious syntactic features such as capitalization. So you cannot say just so the model cannot depend on things like capitalization, location of the token in the sentence for producing the answer. So given that we have defined the reasoning steps a model should perform, we want to test what reasoning steps a model does indeed perform. And to test this, we use the last reasoning steps, value comparison for comparison and coreference resolution for coreference questions. And the reason we do this is the last step, it implicitly relies on the correct semantic parsing of the question and the context, and referential equality in our data that's kind of largely trivial because the entities in the question and the context, they have the same surface forms for the most part. So we will use the two post-hoc interpretability methods for understanding model reasoning. One is attribution methods, which I think we have already discussed. The saliency methods are essentially attribution methods, and counterfactuals. Um, so as we discussed already, so the attribution methods will provide a scalar saliency score for each token in the context, and that will tell us how important that token is in the model decision. But there is a problem in transitioning this to model reasoning. So you can see that example, the sort of the green tokens are the ones that the attribution method finds important for the model's decision. But why is this token which important? Is it because it is the first token, or it determines the answer entity type? So fortunately, in our case, the problem is kind of solved by design, because for each reasoning step, we can define a positive and negative partition of the token space that the model should find important if it follows that step. So I'm showing an example for the value comparison step and which tokens the model should find important. And the paper does describe this for the other steps. But our assertion is that if the model follows the reasoning step, then the average saliency score in the positive partition will be sort of statistically significantly higher than the negative partition. So that's one way of saying that the model, if I have a bunch of questions and if I have a bunch of instances, and on each of these instances, depending on the reasoning step, I can define a positive and negative partition of the token space. Then the average saliency score in the positive, I want to check if the average saliency score in the positive positive part is higher than the negative part, and in how many cases that does happen. If it happens in a large number of cases, we can say, well, the model is following the reasoning step as expected, as defined by this explanation method, or this attribution method. So there is a problem with that the saliency scores are not always faithful, and when they're defined on the tokens itself. And so they are not. So we talked about faithfulness, right? And so the saliency scores have found not to be faithful when they are defined on tokens, and we are actually aggregating the saliency scores over sets of tokens. So are they faithful or not? We don't really know. So this is kind of, so we use this as like parallel evidence. So this is one sort of evidence, and the other one comes from counterfactuals. So counterfactual methods are methods that perturb an input instance minimally to change the model decision. So while they're so for example, the counterfactual formulation in our case translates to, had the model not relied on some information, let's call it information X, it could not have answered both the original and the counterfactual question correctly. So we are doing counterfactual perturbations on a set of questions, and these perturbations are dependent on the reasoning steps. And we are asking, does the model answer the question correctly in both cases? So for example, if I have to test if the model understand the concept of comparison, I will change that earlier token to later, and I would expect the model to actually output the correct answer in both cases. And if it fails, it should fail on both cases. But if it is correct, it should make the correct answer in both cases. And then for the coreference one is a little more complicated. And what we do is I think I'll discuss that in details in later. But in general, the idea is that in the first example, you see that I is coreferent to goreki, right? And then what we do is we break the coreference cluster, and we introduce a new sentence that produces a new answer. And the coreference, now it has a different coreference cluster. So the model has to depend on the understanding the coreference clusters to answer this question. So one problem with counterfactual perturbations, which is why we didn't. So the reason why did we do the parallel thing actually? One problem is with counterfactual methods that these require like manual perturbations in many cases. For the coreference ones, you need manual perturbation. For comparison ones, fortunately for these cases, you could actually do some automated stuff. But in general, counterfactual modifications are quite manual intensive thing, so we don't want to do them if possible. So but for now we are going to use them as parallel evidences. So we have the experimental setup is this, that we have a very standard machine learning comprehension setup. We have this is followed from the original BERT paper, and we kind of fine tune 5 models of BERT family on 2 data sets. So the models mostly differ on the number of parameters, except for Roberta, which obviously has a different, not different, but sort of restricted training paradigm and different data. The first data set is called coref, which is the second one is a set of comparison questions from sample from 2 data sets. One is called hotpot QA, and the other is called 2-wiki multi-hop QA. And for comparison questions, as I said, the counterfactual generation perturbation is fairly trivial. And so what we do is we identify the comparative adjective or adverb and then replace it with its antonym. For coreference question, by our definition, the model needs to identify the coreference cluster that leads to the answer. So while the answer always doesn't have to be in the coreference cluster, sometimes it is. And we identify those instances and sample 100. And then we manually add a sentence so that the changed answer now belongs to a different coreference cluster. So this is like the process of generating counterfactual perturbations, and we'll see that how the models do on these things. So our first set of experiment, it's basically what we do is we train 3 models from each class and kind of report the F1 and exact match score. And this is common in the MRC literature. And as we can expect, the larger models seem to do better, and Roberta Large has the best performance. And on the positive side, the standard deviation is very low, so we can expect that the models from the same class perform very similarly. And when I say class, this is very loosely, what I mean is basically the BERT, like BERT large versus BERT small and things like that. So then we'll choose the best model from each class to run the explainability experiments. So the first experiment is the counterfactual perturbation one. So for comparison questions, the model performances are very similar across the original and the counterfactual perturbations. And this tells us that the models do follow the reasoning steps as expected. So, but that the same cannot be said about the coreference one, and we'll kind of further explore this later. So for attribution, so for the attribution-based explanations, we use 2 attribution methods. One is IG, and the other is occlusion that we have discussed. And there are kind of multiple design decisions when applying sort of these attribution methods in MRC models. We discussed them in the paper. Our goal was to see if the counterfactual and the attribution explanations aligned well, because obviously the counterfactual explanations require manual interventions and the attribution explanations don't. So in an ideal world, we'd like to use the attribution explanations. So we say that 2 explanations align when both the original and the CF perturbations are answered correctly, and the positive partition has a significantly higher score than the negative one, and significantly in a statistical sense. So we're reporting the percentage of cases where the explanations align. And I think that kind of a negative result is, so one thing is that we did a sanity check. Well, as you can see that in 0% of cases, the positive partition has a significantly higher saliency score than a random partition, which means that this is like this. So the method is at least has some sort of scientific, like some sort of validity. But I think the unfortunate part for me was that I didn't see a good alignment. So, and that can be for various reasons. One is that it's possible that for example, in IG, you don't actually see good alignment, especially in the later ones, in the larger ones. So it could be that the IG scores are not very faithful, or saliency scores should not be. The way we are doing this is that we're aggregating saliency scores over multiple tokens, and so we probably should not do that. And so we do kind of in the paper, we actually discuss the possible explanations, but we we also discuss a very weird situation where we kind of see that paying sort of extra attention or essentially extra saliency to the important tokens might be a bit harmful for generalization. And what we mean by generalization, I'll talk later. So, and this is again discussed in the paper. Now, a part of our definition of understanding was that the models had to use the same strategy in novel contexts. And we saw that, at least in the comparison data set, the models seem to follow the reasoning step. But the question is, will they generalize? And what do you mean by that they will generalize? So if you remember the counterfactual perturbations for the comparison questions, they were generated by replacing the comparative adjective by their antonyms. And previously, these replacements were in domain. So for example, if the original question was who is younger, we would change that to who is older. But both of these questions were in the training data set. Now we change that to who is more senior, which is not in the training data set. So this times the models fail on counterfactual perturbations, and like they don't fail, but they have a significantly less number of cases, significantly less success, which means that the models don't. So comparison is in comparison process. A human would really not be confused by the statement who is more senior versus who is younger, right? So what I we think happens in this models are learning the idea of comparison. So they are learning that you need to, when there is a comparison question, they are learning an algorithm, which is you need to assign, you need to compare between these things, and depending on what token you have for the comparison operation, you need to do a less than or greater than operation. So that algorithm is being learned, but this is very heavily tied to the lexical patterns in the data, so essentially the tokens in the data. But at least what we can see is that there is a sense of reasoning that emerges in, and the models are learning the algorithms that are necessary for comparison questions. So we also increase the, so we did another experiment where we increased the context lengths, and so we kind of see if that does affect the results, but not as much as so if you look at the CFOD in the supporting facts versus CF in the paragraphs part, you will see that the results are not as bad, right? If you increase the context length, so the models do need. So one other thing is that, so this is what we're trying to see, is that is the model like following the proper IR strategy. So if you have just a very simple like examples that I've shown so far, then the model doesn't need to do a lot of IR or like information retrieval to get to the right sentences. But with this change, we are also testing for that information retrieval part. And so we do see that for comparison questions, this actually do work to some extent. So in summary, yes, the models do learn some sort of reasoning algorithm, which is what we would expect in a comparison question. But maybe the algorithm is very tied to the lexical patterns that are used in the data. In other words, tokens in the data. So that was all good about the comparison questions, but obviously the coreference questions that didn't really work. So basically what we can say from the experiment is that the models did not follow the reasoning steps as we defined them. So we can only assume that they're using some sort of heuristics. But so our question was, can we discover them? So a common heuristic for QA problems would be to select a sentence from the context and then select a span from that sentence. And if the model used this heuristic, what would be the performance? So we wanted to test that. So we used different sentence selection and span selection strategies, and they are described in the paper. But the best result we can get is 21.5%, which is much lower than the worst model performance on the coreference dataset we have seen. So the conclusion here is that if the models did indeed use heuristic algorithms or shortcuts, they would be non-trivial to discover. So even if the models did use that, you wouldn't really get to that. So I think that it's kind of a negative result in the way that if you come up with some reasoning strategies that you think the model should follow, you test for them, model, you see that the evidence of the models following them, then you know the model followed them. But if you don't see the model following them, you cannot really discover the reasoning strategies the model might have followed. So at least with the existing one, so definitely that opens up an area for future work. But with the current ones, I don't think there is a good way to find that. So the key takeaways of this paper is that to understand if an NLU is right for the right reasons, we need to define the success criteria rather rigorously and on a case-by-case basis. And the models do need to be tested with meaningful post-hoc explanation methods. And we do provide such a framework for such a rigorous testing, and see that some models do follow the expected reasoning steps, but they perhaps don't generalize very well. And some models do not do that. And it's really hard to find what they do. So when we see that the models don't follow the expected reasoning steps, it's really hard to find what they might have done instead. So that is kind of the end of the paper. And so I think we can go into some discussions that, in general, this work is, so I'm personally interested in explainability work. And I think if you are interested in this kind of work, that's great. What do you think? So we can have a free discussion now. So obviously the presentation is done. We can have some free discussions about your questions about the presentation, or any interesting thing that you think can be done, you personally think that is missing in the current explainability work, and you would like to see that, or some interesting ideas. I'm open to that. So with that, I thank you for listening. And it was for us a long presentation, but I hope we kind of came to a point where we kind of enjoyed the sort of got to know some of the things in this from this work. Well, I hope you enjoyed, and sorry about the long presentation, but I'm going to end here.
Thank you very much. So maybe we can go to the discussion. So maybe I will start that I think that the problems with explainability and interpretability now is like the evaluation of the explanations, because like we have many different methods and like all of them works. So how do we know that this is the right one for us? And the discussion about if the explainability should be right for human, like should it make sense for humans, or maybe not, because models don't think like us?
So I think that's actually a very important question that I've thought about this for a long time. So it's a conundrum, because let's say that your model works in a very weird way, right? And you cannot explain that in a human, in a way that a human can understand. So what good is that explanation then, right? Because then we don't actually, I mean, so I think about it in this way, is that let's say there's like you're playing you have trained a model to play a chess game, right? And you know how you have standard opening moves and kind of moves that you can make when you are in a situation, and the model does something completely different, right? So you as a human do not really see the logical sequence behind these moves, and that might be a faithful explanation, but would this be helpful for humans? I don't i don't know. And I mean, explanations are explainability is a very human centric thing. You want explanations because you want to understand how the model works. So there's always this conundrum of do we like do we make explanations, do, what is a good explanation? Is it the one that is truly faithful to the model, or is it the explanation that has a higher plausibility? So in summary, I don't think there's a good answer to your question, but I can say that what I've started to do is I have started to incorporate different kinds of evaluation mechanisms, because I think like that's kind of the only way to go about this. So if you look at so I think there was a paper by from Graham Newbeck's group, and that's not about explanations at all, but that's about like different aspects of evaluating named entity recognition. So they have like a very varied way of evaluating that, and I think that is, and they have a benchmark for that, and I think it's called, um, I'm missing out the name, but you can search for like Graham Newbeck in your evaluation and it will should come up. And I think we need something like that for explainability. So just saying that, so you have a method, suppose you come up with a method, it's just not sufficient to say that it does well on, um, you know, does well on sufficiency or comprehensiveness. It needs to do well on plausibility and all other things.
Yeah, you're right. Thank you. And the other problem, I think, that we don't really have the methods for explaining generative models. Uh, and I think this is very important, especially now when we have like GPT chat, who's very famous and people are getting into NLP more.
That's true. And so I haven't really worked with generative models as such, so I don't have a good answer for your question. So if you're asking if we do have some good method for explaining generative models, um, I I don't think so right now. At least obviously if your generative model is a sort of statistical model, with a, then obviously you are modeling that in that way, so you do have an explanation. But um, for seek to seek models, I guess attention is the probably the kind of one explanation. But yeah, I don't have a good explanation, good knowledge about exploratory methods used in generative models.
I don't know if you read the paper, but there is actually one paper about when, if and when we can think about attention as an explanation.
Right.
Yeah, I don't know,
So
it's an ACL or something.
so this has been a constant debate, right? So there's this paper is like, so when attention came in, people were like, well, I personally thought this is the what we need, this is the explanation. Then the paper was like, attention is not explanation. Then the paper was like, attention is not explanation. So this has been a fun ride in the attention domain. But I think in general, so these are so I'm not entirely sure about, so in one of the works that we are doing right now, we are looking at sort of hierarchical explanations, and we are generating them from, so to give you a hierarchical example of hierarchical explanation is that, so far we have talked about like tokens, right? But the tokens are essentially a part of a constituent, right? And so what if like but our explanations are token level and not at all constituent level. So we're trying to get to a explanation to methods where which will have this kind of constituent level explanations. And we are using attention weights in some ways. So if you are talking about these papers, one is from the, I think, Byron Wallace's group, and the other is from, I forgot the name, so I think the first author was Sarthak Jain, and the first paper, which is not explanation, and the other one was, I forgot the number, from Georgia Tech. Are these the two papers, or are you talking about something else?
Actually, I don't remember. I think it was an ACL, but I don't remember the authors.
Yeah. So I will. So if you do, if you do find out the paper, do send me, because, it's so I at this point I know two arguments for calling attention and exploration versus not calling it. But if there's been more work on that and I'm not aware of that, it would be really nice to know.
Sure, I will send you the one paper.
Okay.
Yeah, maybe others have something to say. Or if not, I can speak more, because I'm really interested in the explaining NLP. So, Okay, so if not, I can speak. Uh, so, like for me, the practical motivation is like to know uh, why the model decided to use that information. Uh, but I especially like unsupervised learning, so I think it's a bit harder because we don't have the output and like semi-supervised methods, so it may be a bit harder than in supervised setting.
Yes, so obviously, unsupervised and sort of semi-supervised methods, they are, well, so to begin with, so all this discussion was about, you know, the gradient-based methods. They are obviously kind of mapping. There's a clear mapping between the token to a class, right? So sort of sentence to a class, and so that setup gets broken in most semi-supervised methods, especially the ones that are doing LMs and so on. So in, I think it's a very so in general. So let's say, I think BART is, these days BART is quite old, but even if with models like BART or Robota, we have while how to explain the pre-trained process is like, how does the model choose the correct token in the pre-training process, um for the mass token. That's that's I mean, that would be a really interesting thing to know, because obviously we are working on the, like, the fine-tuned models after that model has been used. So one a cup so I guess there isn't really a direct way of evaluating this, but I don't know if you're familiar with probing tasks. Are you?
Yeah, I do.
So right, so the probing tasks are in a way to kind of check for, taking the model representation. So this is not telling you how the model actually did choose a particular token in the mask location, but in once your models are trained, once your pre-training is done, you get the representation from the tokens. The probing tests are somehow trying to see what information might have been encoded in that. So um, I guess sort of unsupervised. So um, the how question in unsupervised or semi-supervised setup, especially in the LLM setup that I can think of, is going to be fairly hard to answer, because I I don't think the methods that we have right now can, the techniques that we discussed, cannot be readily adopted there. So you would still, you can still use gradient based methods, but I don't see how they can be directly applied. So you'd have to probably do some modifications.
Yeah, sure.
But that would be an interesting area. So if you are like looking into that area and want to work in that area, that would be an interesting area.
Yeah, thank you. Yeah, I will try.
Uh, um so I
Okay.
s- if there's no other question, then I think we can end. Well, I mean, thanks for the invitation, and I hope the for people who don't work in explainability, there was some motivation to work in explainability. There will be some motivation to to at least think about explainability on this, after this, and hopefully this was helpful a little bit.
Yeah, it was very interesting talk. Thank you very much.
All right, so I'm going to sign off. Thank you.
Thank you.